All right, everybody. Now that we're finished assignment 61, we've practiced arc length, and that's the one new addition here, arc length. I've got all the rest of our fun, happy friends, and when you get to class, then I hope that you remember that arc length S is equal to r theta, as well as everything else, because you're going to use that formula S is equal to r theta in the next notes. Assignment note 6.42, angles and rotation, day 2. Let me talk about this gigantic chart that I have. I wanted to put lots of real examples so that we could know what's going on. Let's focus in on this square right here. If you want to talk about distance, we normally talk about linear distance. Like I've walked 3 miles. I'm 5 foot 10 inches tall. These distances are straight, and they go in a straight line, and they're measured in miles, inches, centimeters, kilometers, etc. And often we use the letter D, but today we're going to use S, because S is the letter that we use when we allow it to be negative also. You could, like a negative distance would be we lost 5 yards in football. So S is the same as D, except we're allowing it to be negative. In physics, it's often called displacement. And someone once told me that the word for displacement in German begins with the letter S, but I never really verified that. If you want to relate that to an angular distance, so over here, there's actually 2 kinds of distances. And angular distance is, you can say, we use these kinds of things all the time, like if you're snowboarders, they do tricks like a 360 or a 540. Like when you land a 540, then that's 1.5 full rotations around. Like your right foot, you go up for the jump, your right foot is in front, you do a full spin, and then you do another half spin, so your left foot is now in front. That's 540 degrees of angular distance you've just rotated, and that's a full send right there. You're adjusting your course in sailing 10 degrees to the left. That's an angular distance we have to adjust. If you said that the Earth rotated 75 degrees about its polar axis, or the moon revolved 90 degrees around the Earth during the first quarter, those are angular distances. And the units that we measure in are degrees, revolutions, rotations, and if we're talking about radians, that's technically not even a unit. It's like 2 pi radians is just really the number 2 pi. It's unitless. But the letter we often use is theta for that. It's just people just try and use theta all the time so we know what we're talking about, because it's used in this formula, S is equal to r theta. Now, the relationship between these two, if you have a linear distance and you want to convert that to an angular distance, we have to know what the radius is. The relationship between these two is radius. Similarly, we know that if we have a distance and we want to somehow relate distance and speed is, say, driving 65 miles per hour, or the tectonic plate that Los Angeles is sitting on is sliding at 1 centimeter per year, we have to talk about units like miles per hour, kilometers per hour, meters per second, centimeters per second, etc. And the letter we often use is R for rate. But that's just going to be super confusing with the radius. So for today, we'll use V for velocity. And that actually makes a lot of sense, because we want V to allow V to be negative as well. In fact, my physics teacher from high school would cringe at this textbook, because they say speed all over the place, and what they really mean from a physics standpoint is velocity, because they're allowing it to be negative. I bring that up because this is not new, but I wanted to say that you can relate these two with time. If you've got a time and a speed, then you can find the distance. Or if you want to find if you have a distance and the time, you can find the speed. Like if you have any 2 of these, then you can find the third one using these formulas. And this is not new. This is sometimes it's written as D equals RT, or displacement is equal to velocity times time. And sometimes it's written like this, but these are just reorganizations of the same thing. And of course, we're not using R for rate. We're going to use V instead, because we want to reserve the letter R for radius. Now, here's a new thing. Here's a new idea. You could go, just like you have a linear flavor of distance, you could also have an and an angular flavor. Like there's two kinds of distances, linear and angular. You could also have two kinds of speeds, a linear speed and an angular speed. And so here's some examples of angular speeds. You could say that the Earth orbits the Sun at 1 revolution per year. Or a Ferris wheel rotates at 6 degrees per second. Which one's going faster? Which one has a higher angular speed? A Ferris wheel, definitely. 6 degrees per second, that's way faster than the orbit of the Earth. Or a record player operates at 33 RPM. The speed on that is real critical, because if you speed up a record player, it starts to sound like Alvin and the Chipmunks. Or if you slow it down, then it just sounds like this. Anyway, car engines have got to be... You want to be able to rev that exactly to the precision you need, and car engines have got to be very careful. And it measures at 1,000 RPM on your tachometer. Right next to that, there's a dial on your dashboard that tells you the linear speed that your car is going at, like 15 miles an hour, 60 miles an hour, 85 miles an hour. And there's also another dial that tells you how fast your engine is moving. And it's usually measured in RPMs. That's an angular speed. The units on this are usually rotations per minute or degrees per second, or per hour, because there's actually technically no unit here. We can say radians per hour, but it's measured in per hours. The letter we often use is called omega, and it looks like this cursive W. You can write a cursive W if you want, but this is what it is. Now, just like S is equal to R theta, V is equal to R omega. It's structured the same way. And the relationship between the two, you've got to use time. Like if you have any two of these three things, then you can find the third. If you know the distance, the angular distance, and the time, you can figure out what the angular speed is. Or if you know what any two of these three things in this equation, and that's what you'll need. You could extend this table downward even more. Distance, velocity, acceleration, force, torque, say force or momentum. Those are all linear, and they all have angular flavors. There's angular acceleration. That's how quickly do you go from 0 to 5,000 RPMs on an engine. An angular force is applied by a wrench or a screwdriver to undo a screw. That's called torque. Angular force is called torque. And there's also angular momentum too. But we're just going to talk about these four, although in physics you can extend up. And same as before, I want to caution you that you have to use radians for theta and W. So make sure these formulas only work when you're talking about radians. You have to add in an additional conversion factor if there's not radians. And then same as before, let's make sure that all of these linear parts, they all have the same units. Like let's make sure they're all measured in meters or all measured in centimeters. So let's do an actual example. Check this out. An Earth satellite in its circular orbit, 1,200 kilometers high, makes one complete revolution every 90 minutes. This is actually kind of accurate. The space station will go all the way around the Earth every hour and a half or something like that. It's ridiculously fast. What is its linear speed? Use 6,400 kilometers for the length of the radius of the Earth. So we know that the radius of the Earth is, from the center of the Earth up to here is 6,400 kilometers, plus you're going to go an additional 1,200 kilometers, so for a total of 7,600 kilometers. Then we're also going to know that we go one revolution in 90 minutes, and I'm going to convert revolutions to radians. So one revolution is equal to 2 pi. And I'm not even going to write the radians because it's unitless, but one revolution is equal to 2 pi in 90 minutes. So we want to find the linear velocity. So we look in our formula sheet and we see that linear velocity is equal to radius times omega. That's angular velocity or angular speed. So we've got r, that's 7,600 kilometers. Remember, that's the total radius from the center of the Earth all the way up to where the satellite is, and then we're going to multiply it by its angular speed, which is 2 pi per 90 minutes. So taking this given right here, this known, and turning it into 2 pi over 90 minutes might be the trickiest thing. But once you multiply these two together, you get, on a calculator, you're going to get, notice there's no units here, so the units are going to be kilometers per minute, 531 kilometers per minute specifically. An anchor is being hoisted at a rate of 2 feet per second. The chain would being wound around the capstan. Here's the capstan right here. That's the thing that winds up the anchor. With a 1.8 yard diameter was the angular speed of the capstan. So we know that linear velocity is 2 feet per second. It's going up at this 2 feet per second. We know that the diameter is 1.8 yards. We know the radius is so therefore when you cut it in half, that's 0.9 yards. And I see feet here in feet per second, so let's change that to feet. Let's make sure we do the whole thing in feet. So multiply that by 3 because there's 3 feet in a yard. We get 2.7 feet. We want to know the angular speed, omega. What's omega? So let's look for a formula of omega. Omega is equal to linear speed divided by radius. And so that's 2 feet per second divided by 2.7 feet. The feet cancel out, and we're left with per seconds. Or if you want to really write it down, you can. Technically, it's not a unit, but we can say it's 0.741 radians per second. Let's see. I wanted to do an example that took us all the way around, as long, like the lengthiest possible way around this chart. And I really like this chart. This helps us just visualize a bit more easily the relationships between them. And we only have one formula here. These are the versions of the formula that don't have fractions. Maybe they're the easiest to memorize. I already know that distance equals rate times time. S is equal to v times t. And we've had this from last video. S is equal to r theta. So this is the analog. V is equal to r omega. And then here's a new one. Theta is equal to omega t. This is kind of like distance equals rate times time, except for angular distance is equal to angular rate times time. Anyway, we are given this, that we're going at 45 miles per hour, and we want to know what the angular distance is that you travel. So let me put it to you like this. If you see on your car, on the dashboard, that you're driving 45 miles an hour, how much rotation does the tire go through in 5 seconds? Between the beginning and the end of this experiment, it's 5 seconds, and we want to know how many rotations did it turn, or find the angle at which it rotated. So first, the most tricky thing, I think, is first making sure that everything is in the same units. I'm given inches here, and we want to find inches and seconds here. So let's convert everything to inches and seconds. So this 45 miles per hour has got to get converted to inches and seconds. We've got 45 miles per hour, and this is miles and miles. They'll cancel out if we choose to put the miles in the bottom, and we know that there are 5280 feet in 1 mile. Then if we want to cancel out feet, we can put feet down here in the bottom. We know there's 12 inches. So eventually the miles will cancel out and the feet will cancel out. We're just left with inches, which is good because we're converting everything to inches and seconds. We have to get rid of these hours, so we put hours in the top, and so then we can choose to put, when we choose to put hours in the top, then we know that's equal to 60 minutes in the bottom. Canceling out the minutes, we've got minutes up here and 60 seconds. I have seen students just say that there are 3,600 seconds in 1 hour. If you wanted to do that, you could and get the same answer. In any case, you multiply 45 times 5280 times 12 and divide it by 60 and divide it by 60, and you get 792 inches per second. I think that would be worthwhile to make sure you can do on your calculator at some point, because these are the kind of calculations you're going to have to do. 792 inches per second. That's 45 miles per hour. It's the same thing. But now that we have the 792 in inches per second, we can put the 792 inches per second here in for velocity or speed, and then the radius is 20 inches. We've got 20-inch radius tires, and we can find omega. I have this memorized, and so then I can fill this in and divide both sides by 20 and get 39.6 per seconds. Or technically, that's really what the unit is, because radians are not really a unit. But maybe it's just helpful to write radians per second. So that's how you go from here to here. but I don't really want to know what the angular speed. That's how quickly the tires are rotating around their axis. That's how quickly they're spinning. We went from linear speed to angular speed. Now let's take this angular speed and go to an angular distance. So if this is how quickly they're rotating, how far are they going to travel? How many degrees or radians are they going to travel in 5 seconds? So we've got a formula for that too. Theta is equal to omega t. Theta, and we sub in what we know, 39.6 radians per second times 5 seconds. We multiply these two, the seconds cancel out, and we get 198 radians, and that's the answer. So this is a 3-step process. Convert everything to the same units, then go from velocity, linear speed to angular speed, and then from angular speed to angular distance to find the unknown, 198 radians. And if you really want to know what that is, that's I'm just curious to figure out what it is in rotations. If you divide it by 2 pi, then you get 31.5 rotations. So that the tire is going to spin around its axis 31.5 times in the span of 5 seconds. That's a lot. Your tires spin like crazy, and they work hard for you. So next time you see a tire, thank them. And next time you're in the Great Smoky Mountains, you can think of me, because that's where I spent my spring break in college several years in a row. Take care. Start to copy your problem list into your assignment, oh my gosh, I can't even talk. Copy the problem list into your composition books and start the assignment 62, and then after all that, I'll see you in class.